Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the third lecture for week number 3 for our course of communication systems. In this lecture, we will be talking about filters. Filters are actually very important component for each of the communication systems, as we have previously discussed in our discussion regarding bandwidth and frequency spectrum. We understand that each of communication system has to be designed to operate at a specific frequency. In order to place the signals in particular frequency band, it is very important to design a specific type of filter to suit the characteristics of that particular band. Similarly, in order to extract a specific type of signal, we need filters to extract the signal at a specific frequency band. So in almost all types of communication systems, filter are essential part in each type of communication system. So we'll be having a brief discussion on the filter in this lecture. So what is filter? Filter is basically a frequency selective circuit, because the filter has different response for different frequencies. So typically we characterize a filter in two types of responses. There are certain frequencies which can be passed through the filter, and there are other frequencies which are rejected by the filter. In other words, the filter allows certain frequencies to pass and filter stops certain frequencies to pass through that particular type of filter. When we design filter, so this filter can be designed as a passive filter or an active filter. The passive filter is actually made of passive component like resistor, capacitor and inductor, and of course these are passive components, so this type of filter do not provide any amplification in the system. However, there is another class of filters which is named as active filters. Active filters, they incorporate amplifying devices in the circuit like transistors and operational amplifiers, and by using that operational amplifier, the filtering properties also are achieved, as well as certain amplification is also achieved. So for communication point of view, normally we focus on these 5 basic kinds of filters. First one is named as low pass filter. As I previously mentioned, that each filter has a characteristic that it allows certain frequencies to pass and other frequencies to stop by the filter. So these types of filter, they are also defined on the basis of which frequencies are being passed by the filter. So the first category that I mentioned, the low pass filter, as the name says, it allows low frequencies to pass through that filter. So it passes only low frequencies which are below a critical frequency, which is in filter terminology named as cutoff frequency. So all the frequencies which are below the cutoff frequencies are passed by low pass filter, and all the frequencies which are above the cutoff frequencies are stopped by this low pass filter. The second category is high pass filter. As the name says, it passes the high frequencies. So it will pass only the frequencies which are above the cutoff frequency. So all the frequencies which are higher than the cutoff frequency will pass through this type of filter, and all the frequencies which are below this cutoff frequency will be stopped by the filter. The third category is band pass filter. The band pass filter actually passes a specific band of the frequencies. So there is a narrow range of frequencies which will pass through that particular type of filter, and all other frequencies which are out of that band will be stopped by the filter. The fourth category is named as band reject filter. Sometimes we call it band stop filter or notch filter. This band reject filter actually stops the frequencies over a narrow band or a specific band. So it will allow all the frequencies to pass except those lying in that particular narrow band for which the filter is designed. There is another category of filter which is named as all pass filters. All pass filters actually pass all the frequencies. So when we say all the frequencies, that means we are at the output side you will be getting all the frequency contents in that particular filter which are present in the input signal. So it will not change the amplitudes of the input signal. However, these types of filter, they are used for some specific phase shift characteristics. So they have some predictable phase shift characteristics. So we, using this filter, we try to adjust the phase of the incoming signals. So let me graphically represent the response or amplitude response of each type of filter that I discussed in the previous slide. Again, I want to emphasize that I am only representing the amplitude response of each type of filter. You can see that this magnitude signs. So we are representing only amplitude response because from filter point of view we are interested in getting the idea which frequency contents are available, which is represented by the amplitude response. However, we understand that the complete response comprises of phase response as well, which is not illustrated in this diagram, but that will be there. So these are the amplitude responses of the four filter categories except the all pass filter. So the first one is the ideal low pass filter. You can see that there is a cutoff frequency which is illustrated here as omega naught. All the frequencies which are below this omega naught, they represent the pass band of the filter. That means all the frequencies which are in this range, they will pass through that filter, and all the frequencies which are above this cutoff frequency, they will be stopped by the filter. So this represents a stop band of this filter. The second category of the filter is high pass filter, which is illustrated here. You can see that again there is a cutoff frequency which is represented by omega naught here. All the frequencies which are below this omega naught, they will be stopped by the filter. So the stop band is actually at lower frequencies, whereas the pass band is at high frequency. So all the frequencies which are above this cutoff frequency, those frequencies will pass through that particular high pass filter. The third category is band stop filter. As you can see from this amplitude response, there is a band of frequencies which comprise the pass band of this filter. So the pass band is starting from a specific cutoff value of omega 1 and it stops at a cutoff value of omega 2. So it has two cutoff values. Typically we say that this is omega 1 is the lower cutoff and omega 2 is upper cutoff. So this filter would allow all the frequencies which are between this lower and upper cutoffs to pass through the filter, and all the frequencies which are below this lower cutoff omega 1 and all the frequencies which are above this cutoff, that is above omega 2, they will be stopped by the filter. The fourth category, the band reject filter, is illustrated in this diagram. In fourth diagram here, you can see that there is a specific band which comprises the stop band, which is starting from the lower cutoff value of omega 1 and ends at the upper cutoff value of omega 2. So all the frequencies which are between this omega 1 and omega 2, they will be stopped by this band reject filter, and all other frequencies will pass through this filter. That means all the frequencies which are below omega 1 or all the frequencies which are above omega 2, those frequencies will get passed through this filter. the most important thing that you should realize in this case, that these four diagrams, which are the amplitude responses which are shown here, they are that of ideal filter. These are ideal filter characteristics. You can see that we can easily identify the cutoff frequency, we can easily identify the pass band, and we can see the stop band here. You can see that the pass band is constant in all cases. The pass band is totally flat, is constant, and stop band is exactly 0 in all cases. However, I want to emphasize that this type of response is actually not possible, because if you look at this response in time domain through inverse Fourier transform, you would see that this is actually related to a non-causal system, and any non-causal system cannot be fabricated practically. So all these responses which are shown as ideal filter characteristics, they cannot be obtained in real world. So you cannot get any specific type of circuit or any specific type of component which will depict this type of response. Practically the responses, they deviate from this ideal response which is illustrated here. You can see I have shown practical responses of different filters which are illustrated here. The first one is the low pass response. You can see that there is a gradual change from this pass band to the stop band, which is illustrated here, and even the stop band does not reach to exact 0 value here. So this response is that of an practical filter. So whenever we design a filter, the response would look somewhat like this. If we can make this response closer to the ideal one, but we cannot exactly obtain the ideal response. However, for most of the practical cases, we can get a response which is closely related to the ideal response for the practical implementation of our system. Similarly, for all other types of filters, you can see that the high pass filter, the response is again not same as the one which we saw for ideal response. You can see that there is a gradual increase from a very low value, and gradually the amplitude response is increasing, and eventually you get a high pass response after certain cutoff. Similarly, the band stop filter also has this thing. The response does not change abruptly like we see in the ideal band pass filter. For practical cases, the response, the amplitude response is actually gradually changes towards the specific value. So this is actually the pass band of the system. This part is actually the pass band of the system, but you can see that the amplitude response is not constant in the pass band, and it does not reach to the pass band abruptly like we see in this ideal response. And similar is the representation for notch filter. You can see this is actually the stop band of the filter, but the response what you see here, it does not have any specific like sharp cutoff values omega 1 and omega 2. Rather, the response is gradually changing to depict that band reject response. So the summary is, the practical filters or real filters, their characteristics do not quite match with the characteristics of ideal filter, but for most of the practical purposes we can fabricate filters whose response is significantly closer to the ideal response for the practical implementation of the system. Just as an example, we take a look at different passive filters. So passive filters, as I mentioned, they are made of passive component like resistance, capacitor and inductors. So one of the common filter that we use in communication systems is RC filter. RC filter, they are made as a combination of resistors and capacitors. and by using different combination of resistors and capacitors, we achieve a desired frequency response of the system. RC filters, they are often implemented as low pass or high pass filters. Practically those RC filters, they are actually they behave like a frequency dependent voltage divider, and the voltage dividing function, they provide the specific response whether it is low pass or high pass filter, depending on where do we observe the output of the system. Let me show you different types of filters. So first we illustrate the RC low pass filter. This is the basic definition of low pass filter. A low pass filter is a circuit that introduces no attenuation at the frequency below the cutoff frequency, but completely eliminates all the signal with frequencies above the cutoff. This is the definition for ideal low pass filter. But practically, as I mentioned, that there is certain deviations from this ideal response. So low pass filters are referred to this is the illustration of low pass filter. You can see that we have used a single resistance here and a capacitor here. The input voltage is applied at the resistance side, and output voltage is obtained across the capacitor. So basically, whatever input voltage is applied, it is divided between this resistance and capacitance, and the whatever voltage is occurring at the capacitor is obtained as a filter output. And if we plot the response of this ideal low pass filter, it looks somewhat like this, which is shown in the diagram here. You can see that this blue line, this one is representing the pass band of the filter, and you can see that gradually this band, the amplitude response decreases, and eventually you will end up at the stop band of this filter. So you can see that this filter behaves like a low pass filter, and of course the low pass filter should have a cutoff frequency. As we know that this filter do not have a sharp cutoff frequency, so the rule that we use to calculate the cutoff frequency is the 3 dB rule. So whatever value you have here at the maximum point, whenever the amplitude is decreased by 3 dB, so whatever is the minus 3 dB point, at that point you whatever frequency is there, this frequency is named as cutoff frequency. And for this type of low pass filter, the cutoff frequency is calculated to be 1/2 pi RC, and this cutoff frequency actually occurs at the point where the capacitive reactance XC becomes equal to the resistance which is used in this system R. So by you can see that this cutoff frequency is dependent on the value of resistance and capacitance, and by choosing the appropriate values for the resistance and capacitance, you can easily design a filter to meet a specific cutoff frequency criteria. Similarly, we can have a high pass filter. Actually, high pass filter can easily be fabricated by this RC circuit. The only thing you need to do is to get the output voltage across resistance rather than capacitor. So one simple combination of the high pass RC filter is this one, where this side is actually input voltage and this side is the output voltage, Vout. So you can see that we have only switched the positions of the resistance and capacitance, and now we are getting output across the resistance of the system. And this resistance, this configuration of this RC system gives a high pass response with the cutoff value to be equal to 1/2 pi RC, as I showed before. Similarly, we can get the high pass response by using an RL circuit as well. So if we use a resistance and a inductor in this voltage divider configuration, we can have a high pass response of high pass response for a RL filter. The cutoff frequency for this RL filter is given by this expression R upon 2 pi L. Again, this cutoff frequency is calculated by the same principle that the inductive reactance would become equal to resistance. So you can calculate the cutoff frequency by using this relationship. RC filter can also be arranged in such a way that they depict the response of a notch filter. However, the fabrication of notch filter requires multiple capacitor and resistance to be adjusted in a specific fashion. A simple notch filter implementation is named as parallel T or twin T implementation, again with this cutoff frequency of 1 upon 2 pi RC. This circuit diagram illustrates the implementation of the notch filter. You can see that we have kind of double configuration of this R and C. The shape of this circuit looks like T, so that's why it's sometimes named as parallel T system. So the response of this RC notch filter would look somewhat like this, which is illustrated in the diagram here. Another class of filters is actually named as LC filter, where we use inductor and capacitors to get the response of the filter. And generally these LC filters, they are very commonly used at relatively high frequencies, that is radio frequencies. So radio frequency applications, they generally use this type of filters, LC filters. There are certain terms which we use in conjunction with filters, but I would quickly define those terms so that you have a basic idea whenever we need to use those terms. So first term is the pass band of the filter. As I showed in previous diagrams as well, pass band refers to the range of frequencies which can pass through a specific type of filter. Similarly, another term is the stop band, which refers to the range of frequencies which are stopped by the filter. So the entire band which are stopped by the filter, that is named as stop band. Attenuation is actually the amount for which the stop band frequencies are reduced to certain value. For example, if I go back to the previous case, you can see that so this filter, the stop band frequencies are reduced to a value of minus 23 dB. So this value is represents the attenuation obtained by this particular filter. Insertion loss, as we know that all the circuits whenever they are used in any system, they exhibit some loss in the system. So similarly, each filter, whenever it's incorporated in a system, it also provides certain loss whenever a signal passes through that particular filter. So the loss when the signal passes through the filter is named as the insertion loss. Impedance is actually the resistive value of the load and the source termination of the filter. So whatever, so impedance has the same concept as we use in other courses as well, that it represents the resistive value. Of course, it will be complex because it includes the effect of both resistance and reactance. Ripples is the term because as I mentioned, in real filters the response in pass band is not constant, so there are certain variations in the pass band. So those variations are generally named as ripples. The shape factor is actually because in band pass filter we use two frequencies, the lower cutoff and upper cutoff frequencies. So the ratio of those frequencies is generally named as the shape factor. Actually this is the ratio of stop band to the pass band, stop bandwidth to the pass bandwidth, of the filter. Whenever we represent a filter in frequency domain, so there are certain frequencies where the impedance of the circuit becomes very high, or mathematically it tends to infinity. So all those frequencies where the impedance becomes very high, they are named as poles of the filter. Similarly, there are certain frequencies where the impedance of the circuit becomes close to zero. So all those frequencies where the impedance is zero, they are named as zeros of the filter. Envelope delay or time delay is actually related to the time taken by signal to pass through the filter. Whenever we apply a certain signal at the input side of the filter, it takes a finite amount of time to appear at the output side. So whatever time it takes to pass through that particular filter is named as this envelope delay or time delay. There is another term which is called roll-off factor or attenuation rate. It refers to the rate of change of the amplitude with respect to frequency in the filter. You can see it here, this amplitude is changing. So how fast this amplitude is changing, this is depicted by this roll-off factor of the filter. So we are done with defining some basic definitions. Now let me try to describe few types of the filter. Actually, I mentioned that there is difference between ideal filter and real filter. So this diagram illustrates a difference between ideal passband filter and the real passband filter. You can see that our ideal passband filter, you have specific cutoff frequencies which are illustrated here, lower and upper cutoff frequencies. They have a specific passband which is shown here, and you can see that the passband has a constant amplitude and the stop band is actually zero, so it is represented here. However, in practical cases, this is not true for practical cases. You cannot get a specific cutoff value, rather the response changes gradually. You can see it from here and here. The response is gradually changing. So eventually between passband and stop band there is a transition band as well, where the response gradually changes from a high value to low value, or from low value to a high value. Second important difference is that the passband is not constant. You can see that there is some changes. The amplitude here is different than the amplitude here is different than the amplitude here. So at different points you would have different amplitude response. So amplitude is not constant at the passband. Similarly, stop band does not have exactly zero values, although the response is very low, but it is not exactly zero. The problem is that whenever we try to design a filter, so eventually we have to compromise on something. We cannot get this ideal response, but we can optimize some parameters. So say for example, if we try to increase this transition, decrease this transition bandwidth, because we want to have a narrow transition bandwidth, so eventually it will cause more ripples in the passband. If we try to reduce the ripples in the passband, we may get ripples in the stop band. If we try to reduce ripples in the stop band, we may get a wider transition band. So what I want to explain is that it's not possible to get all the optimum values simultaneously. Eventually you have to compromise on something. So depending on the type of the compromises that we make in design of filter, and depending on the type of response that we get from the filter, we have defined certain types of the filter. So the commonly used filter, they are characterized by different types depending on the nature of the output that we see from those filters. So let me quickly summarize some basic types of filters here. The first one is the Butterworth filter. The Butterworth filter has a very good property that in pass band it do not have significant ripple. So the pass band is almost constant for Butterworth filter. So that is why it's sometimes called that it's a maximally flat pass band filter, because the pass band is almost flat for this type of filter. Let me show the response of this filter here. You can see this green line represents the Butterworth filter. You can see that the green line has almost same value for entire pass band. The pass band is almost constant, and you can see that even in the stop band there are no ripples here. It gradually decreases to the stop band. However, it has a relatively large transition width. You can see that the transition width is very large. In communication systems, Butterworth filter is most commonly used, because in many communication systems our requirement is to have minimum ripples in the pass band. So that's why you would see in your subsequent courses as well that the Butterworth filter would be very commonly used in many different systems. However, we have other types of filters as well. For example, another filter is named as Chebyshev filter. This filter has extremely good selectivity, that it attenuates the response outside the pass band, means the stop band is quickly attenuated, but it has a drawback as well, that it gives ripples in the pass band. Let me quickly show the response of the Chebyshev filter. So this orange line here, you can see this is actually the Chebyshev filters curve. You can see that it has a very sharp transition here. The filter response gradually sharply decays to the stop band. So it has a very narrow transition band, but it has ripples in the pass band. You can see that there are certain ripples in the pass band which are depicted by this response. Similarly, there is another type of filter which is named as elliptical filter. It also provides good attenuation. It has better attenuation as compared to the Butterworth filter. So the response outside the pass band gets attenuated very fast, but it has high ripples within and outside the pass band. You can see the response here. The elliptic filter is represented here, like with this blue line. You can see that it has very fast decay. The response decays very fast, but there are ripples in the stop band as well as there are ripples in the pass band. Another filter is named as Bessel filter. It has the property that it contains it provides a constant time delay in the pass band. It can be fabricated as low pass or band pass filter, but it always provides a constant time delay for the all pass band components. The response of the Bessel filter is represented here. This red line represents the response of pass band. You can see it has a large transition band, but it has smaller ripples here and smaller ripple here. But in addition to this thing, it has a property of providing a constant time delay in the pass band. So different frequency contents, they experience the different delay when they propagate through this type of filter. So you can see that all these filters, they are representative of low pass filtering, because all of them, they have pass band at low frequencies and they have stop band at the high frequencies. But the types of filter, they show that what type of compromises or what type of deviations from the ideal response we get in the implementation of that type of filter. So with this, I would conclude the discussion on the filters here. I tried to provide a basic introduction of different types of filter and how their responses deviate from the ideal response, and how do we get different responses for different types of filters. So we will stop this lecture here, inshallah. Thank you all.